Okay, should we start?
Yes.
All right. Okay, so we were talking about the secant method. So remember that in the open methods, first of all, we talked uh, about the simple fixed point iteration method. Then we talked about the Newton-Raphson method, and then we are talking about the secant method. So in the Newton-Raphson method, we last time I identified that there was the drawback that this Newton-Raphson method will be difficult to use if you cannot easily find the derivative of that function. So in that case, we cannot use Newton-Raphson method very efficiently. So the variation in the Newton-Raphson method has been proposed in the form of the secant method. So in the secant method, we do the similar thing as for the Newton-Raphson method, but we find we try to approximate the derivative of the function by the numerical methods. So let's see it with the help of this example. Here. So in this case, if you have the same example as we have tried in the previous two methods for a function of e power minus x, now we try the initial estimates at 0 and 1, okay? And we have already used this true value of 0.56714329 and then so some numerical more digits. So in this method, in the secant method, we have the formula for the approximation of the roots. Xi plus 1 is equal to xi minus xi minus 1 xi. So in this case, if you see that this formula determines the next iteration from the previous two iterations, okay? So we have arbitrarily chosen these starting values x minus 1 and x0 is equal to 1. And recall that for x is equal 1 is x minus 1 is equal to 0, the value of the function is because this is 0, so it will be 1 minus 0, so it will be 1, and for 1 it will be for e power, so it will be some other value. So let's find the solution. So in the first iteration, you see that the x minus 1 is equal to 0. This gives us the value equal to 1. For x0 is equal to 1, this gives the value of minus 0.63212. And from these two estimates, we find the value of x1. x1 will be then equal to the value of x1, xi, okay, xi plus 1, and then it will be xi, and then that means this value. So if xi plus 1 is 0, sorry, xi plus 1 is 1, then that means I is equal to 0, so it will be x0. So this value will come over here, 1, and minus, which is in the formula, function of the value of the function at xi. So this means whatever the value over here, the value corresponding to the here, it will come over here. And then times xi minus 1 minus x0. So it will be 0 minus 1 and divided by x minus 1, that is 1 minus fx0. So it is 0.632. So in this way, we will get first approximation is equal to 0.6127. And when we compare it with the true value, the true percentage error is 8%. Okay. So similarly, we can have the second iteration, but and then we get a true percentage error of 0.58%. And we can have the third iteration. In this case, the true percentage error will be 0.0048%. So you can see that this method converges rather rapidly. But remember that although in the first case, which we have chosen these values, that the values of this function, okay, in the first iteration, we have chosen these values x is equal to 0 and x is equal to 1 in such a way that the values are bracketing, okay, that means around, because fx minus 1 was greater than 0, fx 0 was less than 0. Okay, they are of the opposite sign. However, this is not necessary. Okay, this is not necessary in this method, but it is by chance that we have done like this. But by doing this, we are fusing the second iteration in this method, where both the values of the function at both of these approximated values are on the same side. So therefore, this method is here. This method is different from the bracketing method, especially the false position method. In the false position method, we have the same kind of we have the same formulation, but in the false position, we always make sure that we bracket the solution. But here, we do not bracket the solution. Okay. So we don't have to be very mindful of bracketing the solution. So anyway, in this case, in this particular case, the solution is converging. So maybe we can see it in Excel about this. Maybe I can open some new sheet. Yeah, so maybe I can open in the new sheet. So for example, if the first iteration, okay, I is 0, 1, 2, 3. Okay. And the values of xi were, okay, so first we took the value of xi was 0, and maybe we don't need to write it. First we took the values of xi was 0, then was 1, and then we calculated the we need to calculate the f of xi, okay, f of xi. So f of xi was equal, because the function, remember that the function was e power minus x minus x, okay. Now, can you see this Excel file on the screen?
Yes.
Okay, so it is e power minus x, so it is exponent of minus x, okay, minus x is this, and minus x is this, okay. So this was 1, and then this 0, and now this is here, okay. For this is 1 and 0 minus 0.632. So if you see that, we have the same 1 and minus 0.632. Now in Excel, if I apply the formula for the secant method, so what I will do is I will first take this value and minus I will first take this value and then minus the value of the function at xi, okay, and then times the difference between x0 and x1, and then divided by the difference between the functions. So 1, and then these two functions. So Here it is like this. So I get an answer is equal to division by 0. So maybe I have made a mistake. So let me check what mistake I have done. Okay, so I try it again. 1. So I take, because if you see that the formulation is here, okay, I take xi minus this function, then the difference in the x values divided by the difference in the values of the function. Okay, so maybe I try again. I made some mistake. So equal to this. So this value, okay, and minus the value of the function. The value of the function is here, times times the x values, x minus the second value of the x, bracket closed, divided by the value of the function at x0 minus the value of the function at here. So 0.6127. So now I have applied the formulation correctly. So you can see that I don't know why it is covering it. Anyway, so I have applied this formulation. Then I calculate the value of the function. So it is now 0 minus 0.07081. So 6127 minus 0.07. So I have got the same answers for the. So one thing is that I got 0.6127, and then the second one is that I got FFX1 0.07081. I got the same answer. So now if I go back over here, so now I can see that I will use these pair of values. So now you can see that the values of the function at both of these values are negative. So in the false position method, now if I was using the false position method, I will take this and these two pairs, okay, for the next approximation. But now in the secant method, I will use these values for the next approximation. So now simply because I already set it up in the Excel, so I will just drag and then I will get the next value. And the next value is here. It is now 0.00. So this is the first iteration. Okay, this is the first iteration. That means I can say that first iteration is here, second iteration is here, and then the third iteration is. So I check it again, and then I get this, and then now I get this. So now you can see that the f of x is very close to 0 now. So what is the true percentage error? So true percentage error is equal to, for this we need to find the true value. So the true value is, we already found several times before. Let me note it down. The true value was, sorry. The true value was 0.5714329. 0.5714329. So the true value was true value was 0.5714329. Okay. Yeah, we have 0.5714329. 5714 56714,329. Okay, 0.56714. Yeah, here. So if I compare these values with the true values, so then I can find. So the formula for the true percentage error is this is equal to the true value. So the true value is here, and we will fix it minus this value, the estimated value, divided by the true value, and multiplied by the 100. So we get this. So maybe I can take the absolute of this value. Okay, absolute percentage error, absolute. So it is 8.03%, and then for the next one it was 0.58%, and for the next one it was 0.004%. So you can see that we got the same answers. Okay, 0.56717, and like here in the first, second, and third iterations. Second iteration, yeah, and the third iteration, we got the value of 0.56717, and the true percentage error is 0.0048%. So we can see that same values over here. Okay, so this was the illustration of the method of the or illustration of the secant method. Okay, do you have any question?
No.
Mm-hmm. Okay, so now let's compare the convergence of the secant and the false position techniques. So maybe we try to, in this example, we try to illustrate the difference between the secant and the false position technique. Okay, so can you tell me what is the difference between the false position and the secant method?
Maybe in false position we should bracket the.
Yes, and how about in the secant method?
It's not necessarily to be.
Yeah, so this is the main difference. Okay, so otherwise the formulation of both methods is same. Okay, so use the false position and the secant methods to estimate the root of this f of x is equal to log of x. So this here we are using the different approach, different function for the estimation purpose. So start the computation with the values of xi minus 1 is equal to 0.5, and xu is equal to xi is equal to 5. So remember that the terminology is a little bit different in the false position and the secant method. In the false position method, we use xl instead of xi minus 1, and in the secant method, and we use xu in the false position method, and in the secant method we use xi. So we have taken these two choices because you can see that for the false position method, one of the value of the function should be less than 0. And so in this case, for 0.5, log of 0.5 will be less than 0. Okay, because the value of the log for any value less than 1 should be a negative number. So so that we can apply the false position method for this approach. So by the false position method, we can use the equation in the 5th chapter, but which is of the same pattern as the secant method. Okay, the pattern of the equation is the same. Okay, then if we apply this method, then we get these results. So let's do it on Excel. Okay. Okay, so in this case, maybe I can start from xi. Okay, xi is 0.5, and then it was 5, and the f of x was is equal to log of x. I don't know, log, yeah. Excel use ln function for the natural log. So log of x was this, so it is minus 0.69, and then for 5 it is this. Okay, now we will apply the method of the false position method. Okay, so if you see the formula, how the formula works out for the false position method. So we take the xu, okay, minus the value of the function at xu, then we take the difference of the x values, then we take the difference of the function's value, okay, from the lower to upper. Okay, so it's the same, and the formula is on the same pattern as we found in the secant method. In this false position method, now you can see that we can apply this false position method because one of the value for the function is negative, the other value is positive. So for the false position method, then I will take this 5 first, okay, and then I will take the value of the function, and then I will multiply by the difference of the values in x. So starting from xl minus xu, I will close the bracket, and then I will divide by the value of the function, divide by the difference of the values of the function. So I will take the function xl first and minus function xu first. Okay. Yeah, I have somehow my Excel hides these values when I am taking it. So, but you have to be careful. So in this case, what I get is 1.85463. So then for this, I can estimate the value of the function. Okay, so in this case, because we know that the value, the true answer is 1. So the true error is, in this case, true percentage error is, because for log of x, we know that log of 1 is 0. So the exact answer should be 1. Okay, so the true percentage error will be equal to, we already know that it is 1. True error, true value minus this, divided by the true value multiplied by 100. Okay, so, and then we need to take the absolute value, true percentage error. So it is 85 in the first iteration, it is 85.46%. Okay, so for the next iteration now, I think in this, because we are applying the false position method, so we have to take this and these two pairs. Okay, because these two pairs now have the values on the opposite sides. Okay, that means one of the value for the function is minus, and then the other value is plus, because false position method is the bracketing method. Okay, so we cannot, for the bracketing method, we cannot take these two values. Okay, so now in this case, what you do is I take this value first, minus I take this value times, now I take the difference of the x values, and then I close, divide by the difference of the f values. Okay, so now I apply this and I get this value, and the true percentage error is now about 21%. Okay, you can see that the true percentage error is decreasing, but not very rapidly in this case. So now what I can see is, again, the value of this function is plus, and the value of the last known function is negative. So therefore, I have to bracket these two pairs again. Okay, so I have to apply this formula again. This one minus the value of the function is this, times the value of the difference in x values, and divided by the difference in f values. Yeah. So now I get 1.05 and then I get it, and then you can see that now the difference is about 5%. So these are the three iterations: first, second, third. Okay, these are the three iterations. Okay, so here you can see that I got the same values like this: 1.05, 0.05. Okay, so if I see in the Excel, so yeah, 1.05. Okay, and 1.21, and then of course we can go on, then we can further refine it. So anyway, gradually we will reach up to the uh, oh, solution. Okay, so in this case we will gradually reach up to the solution over here. So this is the application of the false position method. However, for this example, now if we do it with the secant method, if we do it in the secant method, so the solution will not converge. Okay, the solution will not converge. So we will get these values. So in the secant method, what will happen? So for example, in the secant method, everything is same, except that we are not bracketing it. So for example, over here, yeah, the first iteration will be same. Okay. Yeah, the first iteration, the results will be same because yeah, because these are the only choices. So in the secant method, now we will bracket, we will use these pair of values for the next iteration. So then I will simply calculate these values, and now I will get what I will get over here is uh, a numerical error over here. Okay, so here we can see that I get minus 0.1048438 over here. So this is the minus 0.10438. So for here, I am get minus 0.10438. And then for this value, you can see that even the function log of x is not defined. So that's why I get the number error over here. So simply speaking, that by doing this approach in this secant method, the solution is not converging. So it means that the secant method will fail in this case. Okay, the secant method will fail in this case. So the solution will be divergent. So this is illustrated by the by this diagram. Okay, so in this case, for the difference of the false position and the secant method is illustrated in this diagram. So you can see that this is the first iteration and this is the second iteration. So first iteration for the false position and for the secant position will produce exactly the same results. Okay, in this case. So in this case, by chance, we have, because for the comparison purpose, we have chosen the values of XL and XU or XI minus 1 or XI to be on the opposite sides of the x-axis, okay, negative and positive. And then these two result, the first iterations produce the same result. However, due to the difference of the methodology, in the second approach, the results will not be, in the second iteration, the results will not be same. Why? Because in this case, for example, in the false position method, we have this XR over here. And then from this XR, value of the XR, so from this value of the, so from this XR, we will move to this point, okay? And now we will bracket this area. So for example, if we move from XR to this point, so this point is over here. So this point will now become XU. And now in this case, because this is the bracketing method, so over here it is plus, the value of the function is positive, and over here the value of the function is negative. So we will bracket this area in this case. Okay, we will bracket this area in this case, and then we will get a more refined result which will be closer to the root of the equation. However, in the secant method, since we have already got this point, so we will now make our next next approximation based on this previous value. Okay, based on this previous value. That means this was the xi value. So therefore, we will take a secant of these two values, and then that secant will project over at this point. So in this case, we can see that now we are moving away from the solution. We are moving away from the solution. So in this case, you can see that the solution is divergent. Okay, solution is divergent. So does it explain the difference between the secant and the false position method?
Yes.
Okay. So therefore we can see that therefore we can see that in the open methods, in all open methods, there is this issue of the convergence of the solution. Okay, so with this thing in mind, so let's see one of the graph for the comparison of the different methods. So earlier we have seen that the bisection method, the true percentage relative error decreases in something like this manner. Okay, it decreases, then increases a bit, then decreases, and then increases a bit, something like this. In the false position method, it continuously decreases. Suppose that for each of the method, the solution is converging. So you can see that we will get the most rapid convergence with the Newton-Raphson method. So bisection, false position secant, and the Newton-Raphson method. So this is this we can illustrate for this function e power minus x minus x. So earlier we have used this function for few of those methods. So by your own, maybe you can try to produce this chart on Excel or even MATLAB. Okay, so you can see that the bisection method is the slowest to converge, whereas the Newton-Raphson method is the fastest to converge. Okay, so next let's use the modified secant method. Okay, so now you can ask that why do we need to consider the modified secant method? Yeah, so the reason is because as we have seen some of the drawback of the secant method, that it fails to converge sometimes. So we can modify this method a little bit by some clever trick. So there is some clever trick. By this, using that clever trick, we can modify this method a little bit, and then we can improve the convergence of this method. Okay, that means we can, for some of the method, if it is not converging, so we can make to converge by using some sort of these modifications in the method. So that's why it is called as the modified secant method. So the modification is done in terms of the choice of xi minus 1 and xi values. So instead of arbitrarily choosing the xi minus 1 and xi values, we can choose the xi minus 1 value as a percentage of the xi value. So that percentage of the xi value is called as the delta. Okay, small delta. We can represent this percentage of the xi value as delta. So in this case, so for example, if we are now taking this example 6.8, we are taking, we are saying that, okay, we take delta is equal to 0.01. 0.01 means about 1% of the value of 1. So if we take x naught is equal to 1 and then we take x delta is equal to 0.01, so it means that our value of xi minus 1 will be 1.01. Okay, 0.01, 1 plus 0.01 will be 1.01, and then let's apply it on for the same function. So in this way we can improve the convergence of this method. So the formulation is similar to the secant method. The only difference is that instead of xi minus 1 minus xi, we are using delta xi. Okay, delta xi means the change in the value of the xi. Uh, uh, we are using the change in the value of the xi. So delta xi means delta is 0.01, 0.0 times 0.01 times 1. So it is 0.01. Okay. So it is not delta xi is not just one variable. It is delta multiplied by xi. Okay. Remember that it is delta multiplied by xi. So delta xi is not just it's not one variable. It is, these are two variables. Delta is one variable and xi is another variable. So delta as a by default we can take as a percentage of some values of xi. So the formulation is same. Okay, like for for the previous case in the secant method. So in this case, then how does it look like? So since the formulation is same, the only thing is that we are the main concept is that we are taking the secant of a very small portion of the curve. Okay, so that means we don't have to take a very big portion of the curve to take the secant. We take a secant of the very small portion of the curve. So in this way, we don't want to move very much away from our original results, but in this way somehow we can get the quicker results. Okay, anyway, so first iteration, and then you can see that in the first iteration we are getting a true percentage error of 5.3%. And if I remember in the secant method, in the first iteration the true percentage error was something like 8%. So it is much quicker than the original method. Okay, so 0.023%, and then it is 0.05%. So let's see. I think it would be in Excel. So where I did it, I did it where? Yeah, here. I did it like this over here. So if I apply the modified secant method, so let me copy these values from here. In the modified secant value, copy here. So in the modified method, what I will be doing is the first value which I will be using is, so for example, let me see what was in the first value was 1, and then the second value will be 1.01. Okay. Okay. So, and the function was same. So yeah. So first value I've used was I will use is 1. And the second value I will take is 1.01. That means I'm just adding 1% of that value. So now in this case, you can see that from the first iteration, I got this value. And then I applied the second iteration, I got this value. And then in the third iteration, I got this value, 0.576. And then you can see that I got the percentage errors like this. So 5.27%, 0.4%. Okay, maybe I can show the full number of digits. Okay, so 5.26, 0.86, 0.39. So these are the same values. So here, so 5.3%, okay. And in the second iteration, it was 0.0236%. Second iteration, it was 0.023%. But here it is something like this. So it is 0.537 and 0.5693. And 537, 0. Yeah, I think I made some, yeah, okay, I need to modify it. It's the formulation is not exactly same. So that's why I'm getting the different results. So, okay, let me do it by, okay, so how I actually estimated it. So I, for the estimate, I need to take this value 1.01. No, okay, I need to look at the formulation, okay. So formulation is, I will take xi, okay, xi is this, so xi is 1, and then I will take the this delta, and then multiply by the 0.632. So f of xi will be this value. So, and then I will take this, the difference between the first values. Okay, so I think now I understand. Okay, so I will take it, okay, like this. Yeah, and also, yeah, there is, we will not have to take this value in this modified secant method, okay? Because we are using the delta, okay? Delta we are using is equal to 0.01, okay? So to correctly apply this method, so the first iteration will be like this, equal to this value 1, the first value, minus the delta. So delta in this case is, we are using 0.01. And then we will multiply the value of the function calculated at fxi, and then we will divide with the value for the function calculated here, okay, which I did not do, but I can do it right now, and minus the value of the function here, okay, and that will be the value. But here, because I need the value over here, so I need to put like it is equal to 1.01, okay, and then the value which is calculated over here was here. So now I get 0.5372, okay, 0.53726, and I get it here 0.53726. And for the next iteration, I will use this value of 0.5372 as the starting value, okay, as the starting value. And then the x naught plus delta x naught will be 0.53726 plus 1% of this value, okay, plus 1% of this value. So yeah, so in this case, I think I need to make some change in the formulation, okay. So here is equal to the first value plus this first value multiplied by this delta value. Delta value is here, and then I need to put it as constant. So it will be 1.01. So now it will be 1.01. Okay, so and then I get the value of the function over here, and the true percentage error is, so the true percentage error, I can just copy the same, no, the formula for the true percentage error will be equal to this, yeah, formula will be same, okay. Yeah, so it will be, the true value will be here, f4, minus the calculated value divided by the true value and multiplied by the 100. Sorry, 100, not 1000. 5.26. Okay, so it is 5.26. 5.27. So it is the same as in the first iteration, 5.3%. So in the second iteration, okay. So now I think in the second iteration, what we have to do is, in the second iteration, what I have to do is I will need to take this value minus the delta. So delta is now 0.01 times the previous value is equal to 0.01 times this value. Okay, and multiplied by the value of the function over here, and divided by we need the value of the function for over here as on the opposite side as well. I think, but then I think I need to make some modification over here. Yeah, it is a little bit tricky over here. So now, for example, over here, so now I will need to take this value plus 0.01 times the previous value. So it will be now this one. So what is the difference between this previous value and this value is that this current value is 1% more than this value. Okay, 0.01. It is not like 0.53726 plus 0.01. No, it is 0.53726 plus 0.01 times this value. Okay, so or simply I can take that this value times 1.01. So for example, I take equal to this times 1.01. So it will be 0.54264. Okay. Okay, so yeah, almost we have finished the time, but I will finish after completing this example. So maybe I will take few more minutes. Okay. So now I have this value. So for the second iteration, now what I have to do is I will need to take this original value minus the delta. So delta in this case is again 0.01 and times delta is in this case is 0.01 times the value of the function. So value of the function was here, and then divided by the value of the function, which for this new case, and minus the value of the function for the previous case. So it is here. Because I did not calculate it, so therefore let me calculate it, and then it will automatically calculate. So it will be 0.59263. Which in fact is not seems to be correct. It is 0.56703, and the reason is because I'm using the wrong value of the delta. Okay, so delta is actually the fraction. Okay, it is the fraction, so that fraction will be 0.5763. So delta x naught is the basically this this value. Okay, that is this 1% of this value. Yeah. In this case, I made the mistake. Okay, so it is delta times xi. Okay, delta times xi. So that's why the value is not correct. So I think I need to correct this value. So here, when I am using this delta, and then it is times. So delta is 0.01, and then times xi. Xi in this case is the value put over here, and then this is times P4, so this is correct. So I hope this time it will be better. Yeah, 0.56701. Okay, 0.56701. Yeah, now it is, the value is correct. Okay, so, and then it is 0.0021. This is the value. And then from here, I can calculate the true percentage error as 0.024. 0.024. So it is 0.0236. Yes. 0.0236. So this is up to the second iteration. So it up to the second iteration, and then similarly in the third iteration we can apply the same process, and then we will find out that we will get the value of 2.365 into 10 to the power minus 5%. Yeah, actually in the end I made some few mistakes, but I think I corrected myself, and then we can further expand this method and can find the third iteration as well. Okay, do you understand or confused?
Yes.
No,
Hello?
it's okay.
Yeah.
We understand.
Yeah, so just, yeah, because the mistake which I did was that, which I earlier mentioned, that this delta and xi are not this not one term. Delta is separate and xi is separate. So you have to multiply by delta by xi. Okay, so that's why you have to do it in each step. So anyway, so that we stop at this point. So this was a little bit lengthier topic, and I am also going a little bit slow. So that's no problem. We still have enough time. So we will continue this topic on Monday, and hopefully we will complete it. Okay.